So welcome everybody, and I also thank the organizer for giving me this opportunity to talk here. So what I will be talking about today is about many-body localization and one particular aspect of many-body localization, which is about dynamical properties in the ergodic phase. So it has already been introduced, the many-body localization, but let me also give you a very brief introduction. So the setup that I will be talking about is essentially this kind of thing. So I will have a 1D chain where a spineless fermion is hopping from one point to one point, and it is subjected to a random disorder or random potential. So this is very simple to understand because this is non-interacting system, and here what happens is essentially Anderson localization. But it means that the sigma DC or the DC conductivity is 0, and all the electrons are localized in certain point in space. And these are the electronic wave functions. So the question of many-body localization is the following: that what happened to this kind of system if I now have interaction between the electrons? So what we have to now think about is not really a real space, but we have to go into the many-body Fock space, where this was the non-interacting part of the problem, but now I have this 4 fermion term. So what this 4 fermion term does, very simply, one can think about it gives a hopping matrix element in the many-body Fock space between these orbitals, single particle orbitals. So now, naively, one would say that if I have interaction in my system, interaction give rise to dephasing. So all the phase coherence which was here due to which the localization was happening will be lost, and naively one would expect there is no localization. However, these two papers came out like 10 years before, and what they said that depending on the matrix element and the disorder strain, there can be a localized phase. Not only that, there can be a phase transition even into a phase which is kind of ergodic or chaotic. The only caveat here is that this phase transition is not a conventional phase transition, but a phase transition which happens in a excited state. So it's not a ground state phase transition as we know from our studies. So this is a phase transition in an excited state or at finite temperature. So the basic thing that we know right now, or at least for these last 10 years, is the following: that this is a kind of a generic phase diagram of this 1D system that I mentioned previously. So this is plotted as a function of disorder and as an energy density. And indeed, there are two different phases. This can be differentiated with many different quantities, like there is no transport here, there is a transport, for instance, area law entanglement, lack of thermalization, and so on and so forth. But what is the most important thing, I think, is following that if I fix my disorder here and if I go through my energy eigenstate, what you see that there is a portion where it is localized. So I have some portion of energy eigenstates which is localized, and then it becomes ergodic. So around this point is the middle of my band, and this thing should continue and cover the whole thing. So that's kind of the generic phase diagram, and there are many ways to distinguish between these two things. So let me give you two basic things that we have worked on. So one way to understand is to look at the eigenfunctions itself. Okay, so if I have a non-interacting system, I know all my eigenfunctions are Slater determinant essentially. So if I have let's say a system size of L and I have L over 2 particles, I know that my Slater determinant will have L over 2 occupations and L over 2 non-occupation. And the way to look at is to look at this kind of correlation function. So these are fermion correlations. I and J are the real space index. So this is a L cross L matrix, and we want to understand the eigenvalues of this L cross L matrix. So this is a one-party density matrix essentially. And what you see that these straight lines, these dashed lines are the non-interacting case. So indeed, half of them are occupied, which showed by they are 1, and half of them are non-occupied, which is shown by 0. Now the question is what happens in the presence of interaction? And it turns out that if I go into this ergodic phase, all these things are occupied in a sense that they are equally occupied and the eigenvalues remain close to half. However, in the localized phase, this still remains like a 1 and 0, and there are only some small deviations from it. So it is still almost like a Slater determinant, but plus some connections. So that's one way to distinguish between these two different phases. The next way to distinguish two different phases is, let's say, look at the entanglement structure. So the way one can look at is what is the entanglement between this point and this point, so or total correlation. And the way to do it is what is known as mutual information. So it's the entanglement of the portion A, which is one side, let's say, is and then again B, and then you subtract the union between them. And what you see already visually that in the ergodic phase, all of the things are localized, all of the things are entangled with everything. So everything is entangled. However, in the localized phase, they are only entangled between nearest neighbor or at max next nearest neighbor. So that's another way to distinguish between these two different phases. So the So in this talk, what I will talk about is mostly about dynamics, so not the static properties, but let's say the dynamics. So what are the dynamical properties in this in these phases? So what is has been understood at least, or let's say there are several works which says that the dynamics in the ergodic phase is not quite diffusive. So they are talking about a sub-diffusion dynamics. So what you see here is many plots, but what is important is this pinkish thing, which is the exponent beta, which tells you how a correlation function decays in time. And if I have a ergodic phase, I know that it should be diffusive, and in the diffusive, this exponent should be half, but this is not what is seen here. So it's half here, but then it goes down, and in the localized phase, so there are many works, and that says that this is due to the Griffith physics. What it means that there are rare region effects, rare regions in the sample, and due to the tunneling, which is very difficult through the rare regions, this subdiffusion comes about. However, there are very recent works which says that no, so this is not quite the story. If you calculate the frequency-dependent conductivity and do a proper extrapolation to omega to 0, you will indeed see that sigma dc is finite, which means that it is diffuse. It is diffusion. So what I will be talking about in this talk, or at least try to say that maybe both of them are true, and I will show you how one can go about it. So the model is essentially same, what I told you. So these are fermions hopping, then there are disorder, density disorder, and then interaction, which is density. I will be working on in half filling. And then for the fine interaction one, the transition happens close to 3.5 at infinite temperature, or at the middle of the band. So now, what is there is in simple terms is the following thing, that I have a sample, and in the middle I excite the sample. Okay, so by excitation I mean, let's say I put up a delta function wave function, and under the time evolution I want to ask how this wave function evolves. By looking at the evolution, I can be able to tell you how the charge transport. So this is essentially calculating the density correlation functions. Good. And what we will be able to do is its energy result, but that's not so important. But the main thing is that we will be calculating a density correlation function. Okay, so if I have a diffusion system, I know that this density correlation function in real space will have a Gaussian envelope, right? So it's a diffusion law. So that's my first results. What you see here is essentially this propagator or the density correlator as a function of length and in a semi-log scale. And what you see is essentially almost a straight line in whichever energy you look at. So this is the ergodic phase. However, we see that it is exponentially decaying function. So this is a weird thing, or something that is not expected. So that's first thing. However, the second thing is that it also moves. So this blue to red is 2 different times, is still moving. So the tail is still moving, however, keeping a shape which is unconventional. So that's the first thing, and which gives rise to probably the subdiffusion that we will be talking about. Now, in order to quantify this thing, I'm going to look at the moments of this correlation function, and especially the second moment, so which gives you how this thing is deviating. And these straight lines, these flat lines are for the non-interacting case. So indeed, for the non-interacting system, as I told you, that this is a localized particle doesn't move from its initial position. So initially, it goes up to some extent, which is the non-interacting localization length, and then it stops moving. So it's a flat line. However, in the presence of interaction, what you see is that it just starts to move up, and these are 3 different system sizes, and in any energy densities, what we see that there is some transport. But now the next task is to figure out what is in which power law this is going on. If it is half, then it's a conventional diffusion. If it is less than half, then it is subdiffusion, and if it is greater than half, then it's a superdiffusion. So in order to do so, what I am going to look at is essentially the flowing exponent, which is just if I have a delta x, which is a power law in t, then I will just look at the log derivative of the with respect to time, and this is essentially the flowing exponent, and this is what has been plotted. So this is a flowing exponent as a function of time. So it's given in terms of length scale, but that's not so interesting. So what you see that with different system sizes, so this is 16, 20, and 24, what you see is that this is no convergence whatsoever. Although it's below half, so what we expect is to go to half, but there is it's still quite a far cry, so it's not really half, but also not convergent. So what we conclude from here, and this is also true for any energy densities, that this is going towards, seems to go towards half, but not quite at there. So what it seems to suggest is the following, that this subdiffusion, what we see here is just a transient behavior and not really the final answer of this problem. So eventually, hopefully, at very large longer time and large system size, it goes back. So why I plot it over here in this way is also interesting, because what is plotted here is the length scale divided by the non-interacting length scale. So at 1 is where my system means my wave packet reaches to the non-interacting length scale, and then only it starts to move. So this is why this is plotted in this way, and only we can go up to 2 times the non-interacting length scale, not more than that, because of the dimension of the Hilbert space and the simulation times. So this is more or less what I want to talk about in this talk. With this, let me thank my collaborator, Ferdinand Evers and Felix Weiner from University of Regensburg, and Giuseppe De Tomasi from Dresden, and these are the essentially the funding agencies. Okay, so this is what I want to conclude, that I told you that there is a non-Gaussian decay of the propagator, which is unconventional. I told you there is indeed a subdiffusion. However, it seems this subdiffusion is transient, and hopefully it goes, it's just an effect of finite size and time. Next, there is a Griffith phase, possible Griffith phase, but it's not so clear, again, because of the possibility of a strong finite size effect. So that's what we propose as our new phase diagram. So indeed, there is a many-body localized phase. There is also ergodic phase. Here, where people talk about subdiffusion, is not. It is there. However, it seems that it is more like a transient behavior and not the final.
This RG studies, right, which gets a subdiffusion. I mean, okay, those are not microscopic models, but still some models where you can get this subdiffusion due to Griffith's regime. So
there could be some model where it can be subdiffusive, but I think the generic picture is that it's a diffusion. And what you are talking about RG is true, but these are phenomenological RGs that are not really, and also the exponent that they give is not quite matching with the exponent that we get out of it also.
Look at entanglement entropy fluctuations. I mean, so
Yes.
there are some results.
So there are new studies that tell you that the entanglement is thermal in the ergodic phase, close to the transition, and there are new studies by David Hughes and all, where they are saying that this is finite size effect. Eventually, it goes to the thermal phase, and this is more or less what I am also saying, but looking at a different quantity, which tells you about the transport. So imagine if it is subdiffusion, it means no transport, right? So then, what transition we are talking about?
So at the largest time you got, it looks far from diffusive, right?
Yes.
But you're saying it, you expect it to go to, or that's not what you're saying?
We have new results which shows that it is turning up.
At okay, and but like if you look at high energy, probably it's easier to. I mean, there also it still looks sub-diffusive, or it should be easier to see the diffusive region.
Large interaction, you mean?
No, if you look at high energy.
No, these are all very high in energy.
Oh, this is already high energy, is it?
Yes. But if you look at so this is, but still it's an energy result thing. So if you look at the full energy spectrum, means like the infinite temperature,
yeah,
indeed you will see that you have to go to a little larger system size and you see that it starts to move up.
Okay. And what system size is this?
Like 26.
26, oh, okay.
So are you saying that even in the regime where it appears sub-diffusive, if you go to long enough length scale, it will be diffusive?
Yes. It's just transient behavior that people are seeing. It's still non-Gaussian, at least in these studies, because I'm still seeing subdiffusion, but the point is that with respect to system sizes, the subdiffusion exponent is not fixed, not converged. It can be non-Gaussian. And even we saw also stretched exponential in certain